Yeah. So before the break, we discussed these kind of relations that you can derive by this trick, which is this kind of directed integration by parts. And these relations between these integrals that that raise these indices by one and create like rational functions in these nus. And in general, they also create rational functions depending on the coefficients of these polynomials down here. They are called IBP relations. And they are also a very big subject of research. And this is so because this is a very big practical problem to resolve these relations. The problem is that for Feynman integrals phenomenology, one has to evaluate these integrals for many different values of these new parameters. And so you can imagine like a big list of Feynman integrals which correspond to these generalized Euler integrals with different indices come in. And you don't want to do the work to evaluate these integrals individually each time again. You want to use these relations to reduce it to a small set of integrals. And this is a complicated task. And in essence, so the third kind of magic property of these generalized Euler-Mellin integrals with these integrals is that you can actually write down a basis of these integrals with which is finite. So if you shift around, so if you raise these indices and you increase them by some integer, then you can show that these relations are powerful enough to reduce everything to a finite set of integrals. And these are the so-called master integrals. So if you have these integrals again, that are as before with some positivity constraints, and the S is appropriate for this to be a proper projective integral, then we can build a vector space. So we build a vector space that has as basis element all the integer shifts of these integrals. So we take this one as a basis element, but also this one, and also this one, and so on. So we take all integer shifts, and it turns out that if we allow the coefficients of this vector space to depend like on these new integrals as rational functions, then the dimension of this vector space we get is actually finite. So M, so in mathematical terms, one writes that this is the span of all k vectors that are some shift vectors. And we have coefficients that are rational functions in these nus. And then we take these coefficients of these new vectors shifted by a k, and the span of all these things. This is so a priori this looks like a very infinite dimensional space, but it turns out to be actually finite dimensional. So the dimension of M is finite. And this is another very interesting theorem on these integrals, and it comes from the fact that these integrals, these functions are so-called holonomic functions. And I'm not going to explain why this is true, but this is like the third main pillar of this theory of these generalized Euler integrals. And the combination of these three theorems that makes this a quite interesting theory of these functions. And you can play these properties against each other in kind of an interesting way. What's very important, for instance, is that you can use this to write down differential equations, also in terms of these coefficients of the p. So you can hit this integral with a differential operator that acts on some coefficient of the p, and then you get a linear. So then this is going to raise like some. It's going to raise the power of the denominator, and it's also going to give you some coefficients in the numerator. And but it stays within this vector space of these integer shifts if you do that. And by just fixing a basis, you can then write down a differential equation that gives you a flow within this vector space of these integer shifts of these functions. This is a very, very useful theory. Okay, so what I want to talk about now is more about the tropical geometry. I've already talked about tropical geometry. So tropical geometry is kind of a simplification of algebraic geometry, where so algebraic geometry you can think of thinking about geometric objects that are defined by polynomials, and in tropical geometry everything is replaced by less information. So we extract like a limited amount of information from these polynomials, and this information is exactly encoded in the Newton polytope of the polynomials. So instead of dealing with all the information that some polynomial has to offer, we want to limit ourselves with the information that the Newton polytope has to offer. And in a way, this first finiteness theorem on these Euler integrals is already a statement then on tropical geometry. And yeah, in this lecture today, in the second lecture today, I would like to explain a bit on how to prove that. So this is now how to evaluate these integrals and to check if they are finite, which is surprisingly equal. So and I already told you how to check if they are finite. You have to check, you have to do this Newton polytope trick. But yeah, there are some improvements if you restrict yourself to Feynman integrals, and in particular to kind of a magic property that these Feynman integrals also have. The key philosophy here is tropical geometry. It's more of a philosophy than a tool, I'd say. The philosophy goes like trying to simplify things into only discrete objects. So try to avoid smoothness work only with discrete objects because computers really like discrete objects. So this is really like a computer-friendly type of mathematics. And with computer-friendly, I mean like 80s computer-friendly, not 2020 computers that can do ChatGPT, artificial intelligence. So this is really for stupid computers that can crank through like tables and lists of numbers and so on, and who are only bothered with complicated concept like real numbers that are transcendental and so on. So the first thing that I'd like to explain for this is why evaluation of these kind of integrals is hard in the first place. And this is also why integration is hard at all. So what is complicated about evaluating integrals? So you might completely justified think if you have an integral, like our Feynman integral, what's the big deal? Why can't we just say, Mathematica, please integrate it for us numerically, and then we are done. So what's the big deal about Feynman integrals? We could write down some integral, give it to a computer. The computer does some computation and gives us out a numerical value. And obviously, we think that people have been working on evaluating integrals for quite some time. The problem is the high dimension of the integrals. So evaluation of integrals in higher dimension relies on essentially only one tool, and this is Monte Carlo integration. So why is numerical integration hard in high dimensions? And high dimension does not have to mean very much. So high means larger or equal to 2, essentially, already for integrals. So it's not very high. And in this case, so-called Monte Carlo integration is the only way to go, or the main way to go. I mean, maybe in 2 dimensions, there's like chances to still work out some other things, but especially if it's seriously larger than 2, then Monte Carlo integration is the only way to go. So how does Monte Carlo integration work? I'm just going to explain it with an example. You probably have some idea on how it works. It's very important in particle physics phenomenology. There are computations being done at the moment by phenomenologists that need like hundreds of millions of CPU hours to evaluate, first of all, Feynman integrals, but then also related phase-space integrals. And these are very costly, and they are, there's lots of computational energy going into the evaluation of these integrals. And maybe these kind of topical tools are, or hopefully they are useful to simplify these kind of computations, because that would save a lot of time and energy, and would also increase the capabilities to make predictions using these approaches. So here's a toy example that I very much like. Actually, not a projective integral, just an affine integral. So let's say this is I going from 0 to 1, and we want to integrate this little function 1 over x plus y from 0 to 1. And if you're very good with integrals, or you type this into a decent computer algebra system, you can find that this is equal to 2 log 2. But we are imagining now that we don't know this, and we want to evaluate this integral sort of the brute force way by Monte Carlo. And how do we do this? It's a simple trick. So we have this space, which is just a square, the unit square, and we have a measure here, and we have an integrand. And the trick goes like that: we interpret the integration as a average problem of a probability problem. So we throw like darts at our integration domain, and each dart hits like some value of x and y, and we evaluate the integral at each of these points, and then we take the average, and we hope that we are getting a good approximation of our actual integral. So what we do by Monte Carlo, so we go to our computer, we don't do it by ourselves, we go to the computer and ask for like millions of pairs x and y that are distributed uniformly on this unit square. So random, independent, and uniformly distributed. So it's of course no problem to organize millions of these pairs, so we can just do it. And then we can try to approximate our integral by averaging over all the evaluations of the integrand over these millions of points. So we evaluate the integrand millions of times, and we hope that this gives a nice approximation of our integral. The problem is that in this particular case, this doesn't really work. And this is also the root cause of problems with these Euler-Mellin integrals. Yeah, so anyone who didn't know the answer before or didn't see this example before know the answer why this doesn't work? Or is it clear why this should work naively? Yeah, so it doesn't work because of the variance. So there's an error term here that goes like the variance over n, take the square root of the variance of this process. So this is a random process. And the variance, it goes like the square of the random variable we look into. And this integral, I mean, it's not quite the same, but effectively it's the same as integrating again over the square. But we square also the integrand. And you can check that this integral is infinite. So here's the divergence. And so the error term, no matter how large the n is going to be infinite. And yeah, so this is a very simple example, and there are many ways to avoid this this issue, of course, in the simple example. But these kind of problems, they are extremely accelerated or amplified in these Euler-Mellin integrals because these are rational functions, and if you square them, their convergence properties are completely different. So you always run into these kind of problems. And yeah, so what, of course, something that you can do, so you can say, okay, maybe this naive Monte Carlo thing doesn't work, but maybe I can go to like a fancy black box computer program that does some fancy things. And these computer programs, they're all named like gambling cities. So you can use Vegas integrator or Macau or everything, and you can activate the super integrator option. And sometimes it will discover these kind of issues and kind of avoid them with some important sampling in the specific direction. But often the difficulty is then that it kind of works. It looks like working at first, but then it again doesn't if you increase the number of points, and it kind of feels random if it's actually working or not working. So I would advise to be very careful with these kind of things. And especially if you increase the complexity of these polynomials that you put in, then you inevitably run into these kind of problems, and you can only kind of shift the barrier where this kind of stuff fails a bit further by using more complicated computer programs to do that. So this tropical geometry can help you around these kind of problems. And with this, you can really properly integrate Feynman integrals. And you can also go to very high loop order with this approach. All right. So the very easy entrance point on how you avoid this is this tropical approximation. So it's just a notational trick, but it works fantastic. So a solution to this problem is this tropical approximation. So if you take a polynomial, again, like sum over the coefficients, and for each coefficient, you have some monomial, then the tropical approximation is just I denoted with p trop. So it's just replacing the sum with a maximum. So we take the maximum over all the coefficients, over all the non-zero coefficients. So the indices, the index sets where the respective coefficients is non-zero. And for this maximal coefficient, so we only take the maximum then over the actual monomials, and we forget about the concrete value of the coefficients. So we only care about AK if it's 0 or not. So as an example, if we have px1, px2, x1 cubed, and then some weird polynomial with some coefficients, then this p trop of the same variables, it's just the function that maximizes the respective monomials. So we have maximum of x1 cubed, x2, x1 squared, and then x3 cubed. So we forget about the value of the coefficients. And here, I mean, just to make clear, so max of A, B is because there was some confusion, it's just a function that outputs A if A is larger than B and B else. So it's a piecewise linear function. But this has a nice property. The approximation property that says that if the coefficients of P are positive, and there are again like some exceptions to this, so we can generalize this a bit and allow also for negative coefficients in certain cases. So if then there are two numbers, C1 and C2, both larger than 0, such that C1 is strictly smaller than the ratio of P over P trop of X, and C2 is strictly larger than this ratio for all X in RP plus n minus 1. And for this to hold, of course, P of X also must be a homogeneous polynomial. So, and also P trop obviously has the same scaling behavior as the original P. So, and this is this nice approximation property. The proof of this is actually very simple. So for the proof, you just choose C to be smaller than the minimum of all coefficients, of all non-zero coefficients. And take the, it's always positive, so we don't need to take the magnitude. And C2 just has to be larger than the sum over all coefficients. And this is something that we can immediately apply to our nice Euler integrals.
Can I make that inequalities for C1 and C2 strict? Or, sorry, can I write S?
You can also make them non-strict. Or what's the question?
In C1 and C2, when you write that inequality,
yeah,
can it be greater than equal or smaller than equal when it comes to the minimum and the sum of the coefficients?
I mean, you can just do this, right? You can also change it to non-strict. I mean, you have to decide what you want to do, but yeah.
Thank you.
So here's the application of this new tool. So again, we start with our Euler-Mellin integrals, or generalized Euler integrals. And we want to integrate them via Monte Carlo. So the trick with which we do this is to just insert this tropical approximation into these integrals. So we just rewrite the integral trivially. And we keep this numerator, but we insert this p trop of x. And we, of course, correct for the error that we made. But now, thanks to this approximation property, we know that this part here is wedged between some constants. So this part of this integral is now moving in some like small interval, not small, but in some interval. So there's definitely no singularities coming from this part. And this part here depends only on like monomials and this tropical approximation, only on this maximum. So now we do a little gambling trick, essentially. So we define our way out of the misery. We define a measure. We just define this measure, mu trop, which is 1 over z. Z is some normalization constant. Over this p trop to the power of s. So maybe I should do like some kind of break here. So this is a definition of this mu trop measure. And I forgot the volume form. So this is a measure on this, sorry, I forgot the plus, on this positive projective space. And it's also only positive because there's no more coefficients. So I mean, I also required the coefficients to be positive of p, but I said there's like some way, some leeway there. But the p trop definitely always has only positive coefficients because it's only the maximum of the monomials. So as long as the x are positive, this is also only positive. And because this part here of the integral just moves in this constrained domain, in this constrained interval, checking if this p trop integral or this measure here is normalizable is equivalent to checking if the whole integral is finite or not. So if we are in the finite situation, we know that this thing here is normalizable. We can choose a z such that this measure actually integrates to 1. So we can choose z such that the integral over rp plus n minus 1 over mu trop equals 1. So we can just normalize this measure. And it's positive, so it gives us a nice probability measure on our space. Now we can use this to just rewrite the complete integral once again. I forgot. Sorry. So we start with the normalization factor z. And here we are just integrating now over this correction term. And the measure is now only this tropical measure over the space. And here we landed now at something very useful because, so if we just think about this as some integration measure on this positive projective space, we are here integrating over something that is strictly bounded. So if with our like Monte Carlo philosophy here, we are never going to run into any problems if we just chuck this thing here into our Monte Carlo integrator. So just explain how this would, to get this over perfectly clear. Just very quick. So the Monte Carlo strategy for these kind of tropicalized integrals would be, so we are now good for an MC Monte Carlo approach. Because we can, in principle, just go to our computer, and of course, this is the main caveat. So go to our computer and say, give us 1,000,000 samples, x1 to xn, capital N being 1,000,000, that are in Rp plus n minus 1, and that are distributed like mu trop, like this measure, then our Euler integral is approximated by this normalization factor z, which we also need to compute over n, and we just average over this the evaluation of this integrand. So this is the tropical approximation over the actual polynomial. This is just correcting like the error we made by replacing everything with this tropical approximation. And then we still get like an error term, but here we have something which is finite. I mean, it's essentially this C1 to the power of S over n, and we take the square root. The important thing is that this is now finite because the variance is bounded. Because if we take the square of this is something, if we take the square of something which is bounded, it's still bounded. So we now have a nice Monte Carlo approach. And of course, here I swept, yeah. So are there any questions to this kind of Monte Carlo idea? Oh. Sure, yeah.
So is the normalization factor normally feasible to compute?
Yes, that's a good question. And yeah, so the question was if the normalization factor is feasible to compute. Yes, so yeah, there are two things missing now. First of all, how to compute the normalization factor and how to sample from this measure mu trop. So you have to teach your computer now somehow to solve these two problems. And yeah, these two problems, they can be solved in general algorithmically by studying actually the Newton polytope of P. So this is an exercise in the tropical geometry of this polynomial P. But specifically for Feynman integrals, there's like a very fast way to solve these kind of problems. And this is because of this generalized permutohedron property that I'm also going to talk about now.
What do you mean by the points being distributed like mu tropical?
Pardon?
What do you mean when you say sample points in the vector space distributed like the measure? What do you mean by that? Maybe it's a measure theory question and I didn't study measure theory, that's right.
Yeah, so this, so we have this, this identity tested that this mu trop, it's a positive weight for each point. So you assign a density to each point in Rp plus in the space. And you want to yeah, so because it integrates to 1, you can interpret this weight, this density as a probability density of each point. And yeah, sampling means that you want to design an algorithm that gives you a point in this original space with probability proportional to the density.
Okay, thank you.
Can you now see like how the variance for this particular probability measure does not diverge like the one in that example? Like, is there like a simpler way of saying it that you don't have any divergence arising from the variance?
Yeah, so this is okay. So here in this example, the variance. So this is why this is true. I can watch that in here. So just think about it. So this is now really like an expectation value. So you can just write it down as z times, maybe in this notation, it's more familiar, p trop x over px. So this is a random variable, and it's defined over this measure, which is given by mu trop. And we want to compute this expectation value. And an experimental way to compute this expectation value is just to evaluate this averaging sum here. But you can, of course, ask, like, what is the variance of this expectation value? What do you expect as a variance if you just do this process here n times? And the variance is just squaring this thing. So what you want to evaluate is the expectation value. I mean, it's not really this, so you also have to yeah, you have to square also the actual expectation value. But this only makes the situation better. So we are just saying this is maybe 0. So this is the problematic term. But because this is bounded by the approximation property,
Perfect.
so we are still in some bounded regime. So the probability measure that we are sampling on it, it's like the important thing. So we are hiding like all the singularities, and the finite, the bounded part is that depends actually on the coefficients of p and not only on the Newton polytope, is something that we just deal with the sampling routines, right?
Okay, perfect. Thanks.
So in order to sample mu trop, in principle, you can use some metropolis algorithm or something like that. Do you really need to know Z to use metropolis algorithm? If I remember correctly,
you need to know it to actually evaluate the integral, but there are also metropolis algorithm tricks to evaluate the z.
Exactly.
The z, yes.
Yeah, in principle, the algorithm should give you Z automatically.
Right. Yeah, I didn't really experiment with like metropolis Hastings algorithms to do this kind of sampling. That would be very interesting to do this sampling via metropolis Hastings.
Thank you.
I mean, what is going to, so this mu trop sampling, it can be done by effectively sampling points that lie inside a certain polytope, which is not quite the Newton polytope, but associated to it. And there are metropolis Hastings algorithms where you are playing billiard inside this polytope. So you start at a certain point and you bounce off the walls in all possible ways, and you get a dynamic process. And it gives you so it's an ergodic process, so it gives you random points inside this polytope. And by the number of bounces, you can also somehow read off the z normalization factor. And the z is going to be the volume of a specific of this polytope you want to sample from. So All right. Any more questions? Yeah, so I'm going to briefly explain. I mean, so I'm not going to have time to talk about this in all generality, but I want to explain how this works, in particular for the Feynman integrals, where you have this, for the Euclidean Feynman integrals, where you have this generalized permutohedron property. Or at least sketch how this works. How the sampling works. I mean, the Metropolis Hastings would be a more fancy way that also works in higher generality, but for these specific polytopes that pop up in the Feynman integral case, there's a nice algorithm that solves these kind of problems. And it's very easy to implement, so that you don't really have to work that much with your computer. You just have to teach your computer a very simple algorithm to generate these points. And yeah, if you do this, you can evaluate. You just have to teach it to evaluate this tropical approximation at this p polynomial, and then you can evaluate Feynman integrals and numerically. And this is also very nice because with this kind of approach, you can evaluate actually very complicated and high loop order Feynman integrals. So because of the simplicity and because of the boundedness of this approximation, then you can go up to about 30 edges or maybe 35. And in phi to the fourth theory, that goes up to like 17 loop or about 20 loop you can maybe even tackle with these integrals. So it's very fast. And maybe it's even fast enough to actually use this for collider predictions, because yeah, for this you also need like evaluate many Feynman integrals very fast, and there are many bottlenecks in this process that are also related to these relations between Feynman integrals. But maybe one can just avoid this by just evaluating the Feynman integrals quick enough for the for these phenomenological computations that need like lots of computer time. So to do the sampling, one key observation, and this is also something that I already mentioned, or to design these sampling algorithms. So this is now the task, right? So you want to design like some algorithms that gives you these sample points and computes you this prefactor here. So the task is now, so there's some intellectual work to do. You have to figure out like how to do this, and you have to teach your computer how to do this. And one approach is to use the property of this p-trop. And a good observation, or a key observation here, is that this p-trop is merely an avatar of the Newton polytope of the p polynomial. So p-trop is an avatar of n of p. So how do we see this? We write p-trop, but instead of the x coordinates, we change to exponential or logarithmic coordinates. So xi is now equal to e to the power of yi. So we write this now in the argument. So this is just a change of coordinates. And now by definition, this is the maximum over all k vectors where the coefficients are not 0. And for each, we take the maximum over all the monomials, but the monomials, they are now written in this exponential form. Yeah. Oh, okay. Okay, I have to be a bit faster. Well, so we can just pull this maximum because the exponential is a monotonic function into the exponential, and we can also pull this product into the exponential. So the exponential can be written, so we can pull out the exponential and write it as the maximum over all the coefficients that are non-zero. And here we have the sum over I, yi, ki. But this is just the dot product of the y vector and the k indices. So you can just interpret this as like as a vector product of y dot k. So this maximum, it sweeps now over all the indices. And if you remember, this is just the definition of the Newton polytope. So we sweep over all these k's where ak is not zero, and the Newton polytope is defined to be the convex hull of all these k's. So instead of sweeping over all these indices of the polynomial, we can also just sweep over the complete Newton polytope. And now we see that actually the only information we need to write this tropical approximation is really the Newton polytope of our polynomial P. And what's important here is that this is also a piecewise linear function. So this is piecewise linear, and it's also called, this function is also called trop of P. So it's also called the tropicalization of the polynomial P as a function in Y. Yeah, so I don't have much time left, but I still want to explain like quickly how to perform the sampling now. So sample from this p-trop, from this mu-trop distribution in this generalized permutohedron case. So the key ingredient here is this generalized permutohedron property. So there are lots of things to say about these tropical functions and about their relations to Feynman integrals, but I want to emphasize now one specific property, namely that there are specific polytopes that are called generalized permutohedra, and they have an inequality representation that looks as follows. So we take all vectors y in Rn, and to write down, so this polytope, it depends on a function z, which is a Boolean function. So it maps a subset. So it's a function from the set of subsets of 1 to n. So this is a function that assigns a value to each subset of 1 to n, some real values. So for instance, z of 1 and 2, which is some subset when n is, I don't know, 3, can be 1, and z of 1 to 3 equals 3, and so on. So this is called a Boolean function. We assign a value to each subset of some finite set. And the finite set is just the integers from 1 to n. So we need such a function, and it also fulfills a specific property, these kind of functions. And we build a polytope from this kind of function, where we sum over all the indices of some set A, and we take the sum of all the y's that are indexed by the elements of A, and we require that this sum is smaller than this value of this Boolean function of A. And we require this for all subsets A in n, where n is the dimension of the ambient dimension. And we also have one extra inequality. So the sum of all indices, then this should be the terminal element, so the maximal, the full trivial subset, which consists of the full set, just determine the sum of these i's. So this is like a homogeneity condition. So these polytopes, so I mentioned that the z also has some extra condition that it has to fulfill. But this is roughly the definition of a generalized pentahedron. So these are specific polytopes that are described by specific inequalities. And the main take-home message here is that Feynman integrals have this property. At least in the Euclidean case, so Feynman integrals with caveats. And in this case, there's a very fast sampling algorithm that we can write down. And I'm going to briefly explain the sampling algorithm still. How many minutes do we have?
We could drop it off in 5 minutes.
Okay, perfect. Yeah. So to do this kind of sampling for these generalized pentahedra, there's a very simple algorithm that does not really involve like any complicated Metropolis Hastings algorithm, anything like that. So it starts by, so we want to sample from mu trop, which is equal to this measure on this positive projective simplex. And to do this, we need some preparation. So we need to build from this z function that has a particular form for the Feynman integrals, but I'm not going to write down. We need to, it's convenient to define a different Boolean function. This Boolean function, I call it omega of A. And there we take the sum over all the nus that are in this A vector minus S times Z of A. So this is just a shift of this original Z function that describes our generalized pentahedron. And then we build a third Boolean function, which is also defined for all subsets. And there we do a recursive definition. We sum over all the elements of our subset, and recursively we take the subset where we remove like one of the elements, and we divide by A, by omega of A with this subset again removed. And then there's a nice algorithm to sample like points from this measure. So we start with A being the complete subset, complete set, and some value kappa, which is 1. Then the first step, we sample like randomly some index out of this A with probability, which is given by this J function. So the probability is 1 over JA, J A with this I removed over omega minus I. So it's very easy to teach the computer to just sample like a random index with this kind of probability. So if you stored this Boolean function in a table, then you set xi equal to kappa, and in the next step you remove I from A, and in the last interesting step you pick a random lambda uniformly, and you use this lambda to rescale kappa. So you rescale kappa with a lambda to the power of 1 over omega of A, and then you go back to 1. And if you do these 5 steps repeatedly, you fill up your coordinates xi. So you have to make this n times until your set A is empty. So if you emptied your set A, you get a complete set of coordinates. And these are distributed as mu trop. And there's also the normalization factor. And the normalization factor is just the value of this J recursive function evaluated at the complete set. So this is how you can do this in this generalized permutohedron case. Right. I'm finished.
All right. I don't think we have time for questions. We're going to come back here in 10 minutes at 12 for the next set of lectures. So let's thank Mishi once again.